There's three of us presenting this subject. My name's Linda Kern-Pelzman. I'm the Director of Academic Program here, but for a couple of decades, I was a math specialist in different schools, and so it's my passion, and I'd love to be able to have a chance to talk about this again a little bit more. Sarah, can you stand up really quickly? Sarah Baxter, our lower school and middle school math specialist, so K through 8, is going to be speaking to you, and Robyn Wise, who's teaching at 7 and 8, grade 7 and 8, and has some interesting pilot programs going on, experimental programs in math that we'll share with you. So just to cut to the chase so you know what we're going to be talking about, I'm going to talk about, in very broad brushstrokes, some of the really big takeaways from what neuroscience is finding in terms of math applications for the classroom. Really big ones. This is the top level one, and I'll point to a few books in case you'd like to read in more detail some of the foundational works. And then we're going to talk about what's actually happening here. So Sarah will show you what we're doing in lower school, and I'm going to talk about middle school. So that's our plan for the talk. And we have time allotted. Okay. So as I kind of given it away a few times, but I'm curious because maybe people responded differently. I mean, these are, believe it or not, the kinds of word problems that you might see in a textbook. It's not impossible. Anybody want to say how they felt when they first read it? I'm just curious.
So I read it and then didn't even try, just checking.
Okay. Okay.
So I read it and I said, oh, I'm only going to base it on one pizza, and then I'm going to extrapolate from it 15.
Ooh, that could be tricky with 16 as your variable. Yes, but interesting. Anybody else? So anybody?
I don't really understand. Those percentages add to more than 100. I don't understand the question.
25%, 66%. Oh gosh, you know what? That's actually a typo. That should be 33. Well, you like a math teacher? Yes, that should be 0.33. Sorry. Well, I'd like to say that I did that on purpose, but
Actually, it overlaps, so it
no, because we said the topics overlapping. And when I changed the topics overlap, that should be 0.33, and then it works. Yeah. So thank you for that. So okay, that's great. Are you a math teacher?
Science.
Okay. All right. So you caught that. Thank you. All right. But now that you know it's supposed to be 0.33, if you want to solve it, then let me know. At the end, but not right this second. Okay, so we, again, I would actually be happy to stay after and solve this with you if you want, because it's really fun, because it's really, for me, this is a problem about hundreds, because of the fact that we have different representations in fractions, percents, and decimals. But the point was just to lead with this as an example of how word problems can often seem to be irrelevant to your daily life, and we all eat pizza, but we don't usually call dominoes and order them in this way, using fractions, decimals, and percents. And if a student was at a point where they understood all of these concepts, this could be really fun. But for a student who might be encountering fraction division for the first time, it would not be fun. And even if they were able to somehow rally themselves to figure it out, it wouldn't necessarily be, it could be, it depends on the student, but it might not necessarily induce the kind of mathematical mindset that you want to help nurture in kids. So I just was reminded of this cartoon that you often see on Facebook, that this is how those kinds of word problems sometimes make people feel. By the way, if anybody feels that I'm being unfair to word problems, please speak up. Anybody want to advocate for the value of the word problems that are in many math books?
No, I think it's accurate.
So what we want to talk about today is how we are all seemingly wired from birth. There are neuroscientists who are now confirming this with empirical studies, even though I think anecdotally, at least as far back as Socrates, people felt this to be true. We're all sort of wired to feel wonder and to be curious. Aristotle said all men desire to know, even too. We're wired for wonder, wired for curiosity about the world, spatial world, world of quantities, and yet somehow we get to this so often. And many Hollywood movies, the classic scene where you're in a class that's hard is math. And in this country in particular, there's a fear of math. And you'll often hear people say, I'm not good at math. And sometimes that's a parent. And they'll say, I'm not good at math, so it makes sense that you're not either. Which, of course, you should never ever say. We'll talk about why. So how does it get from this to this? And there's been a number of studies repeated in different countries, different continents, actually, in Australia, in Europe, this country, where they track the level of enthusiasm for learning generally. You can imagine that for math, the curve is even steeper. Self-reporting. Students come to school, kindergarten on the first day, and they are so excited, right? You can all imagine the kindergartner coming in on the first day with their lunchbox, and they want to learn, usually, after they get done crying because they're being out. And then, what do you think happens as the students self-report year after year? What kind of a curve or graph do you think you're seeing? Well, this is what we're finding. This has been repeated many different times. This is an Australian one. That it literally goes down in a very predictable pattern. And I'd like be interested to read more about why it goes up in high school. I'm wondering if it's academic or other why it goes back up, but the learning changes. So what we're trying to figure out is in the math context, what can we do to change that unfortunately predictable loss of student enthusiasm for school and for math teachers? Now, there's a lot of words up here, and we will share these slides with anyone who would like a copy afterwards. Email us and we'll send them to you, so I'm not expecting you to read these all now. But I want to point out this one book, Why is Math So Hard for Some Children? This was one of the first books to come out after a lot of data had been captured from controlled studies using fMRIs, and of course, probably as I imagine, fMRIs don't dictate how to interpret the data they're seeing. But after a large body of studies, people coming from many different fields looking at this question of what is a math disability as opposed to a math difficulty. And as we heard Ellen Broughton saying this morning about processing speed, right? It's not clear exactly what's causing the variation in processing speed. There's still a lot of questions about what causes a math disability and what a math disability is. This book is a great place to start because it brings in people from so many different fields looking at this problem in different ways. And I just wanted to put that up there for you. However, even with all of that, with that caveat, that there's not an absolute consensus on all of the factors that impact what gets called dyscalculia. There are two things that we do know that can help lay a solid foundation for mathematics success. Two big observations. And you might find them surprising. Maybe not you, because you already know the answer to the problem. But you might find them surprising. One of them is the notion of number sets and the idea that it can be grown. Did anybody ever hear the idea that there's a math gift, where someone would say, you've got the math gift, or you don't, or someone's just good at math? Yep. Well, neuroscientists will tell us now that any biological factor that might give someone an edge, ultimately, in the context of other environmental factors, is irrelevant, or largely irrelevant. That it's not the biological predetermination for mathematical thinking that makes you good at math. It's the training and passion for math that you practice and experience and live. So that's one of the biggest surprises for me, was that number sense can be grown. And I think if you're a teacher of students who you've seen year after year, it's like Groundhog Day, you know, that movie where you might teach a math concept and the student seems to get it and then they don't get it the next day, and even the next year and the next year they seem to get it and not get it. This idea that there could be something underlying all of that there could be a number sense capacity that could be grown that could help remediate that Groundhog Day phenomenon is kind of exciting. And it means that we can never say, for 99.9% of the population, you can't be good at math. Number sense can be grown. And I'm going to talk about that a little bit more in just a minute. The other one, which might be surprising to some of you, is that some of the neuroscientists who are most known in this field, at the end of all their studies, concluded that the number one factor impacting math success is emotion. The emotion that you bring to math, which is, again, I think, maybe a little bit surprising. So these are the two large areas of or takeaways that I want to talk about today. The role of number sense and emotion in math success. And then how can we help to build that? And that's what Sarah and Robyn will speak to. This is just a little bit of a testament to the math bit. So if you're looking for some reading on the subject of number sense, I highly recommend this book, Stan Dehane. He works in Paris. He's widely known and cited by other people working in the field of math disabilities. And he wrote this great book called The Number Sense, which, believe it or not, became a New York Times bestseller. And it's highly readable. It's got wonderful stories in it as you make your way through it. And it's he and his team laid a lot of the foundation for our understanding of number sense. So, for example, one of the questions that neuroscientists have been trying to answer is, do we come hardwired from math? And the answer is yes. There is a fundamental understanding of quantity involving very small numbers, somewhere between 0 and 5, 0 and 6, that is almost understood qualitatively, like the color red or the color green, and that very, very young infants will notice a difference in quantity when tested for their reactions. Obviously, they're not writing the same responses. So do we come hardwired for math? Yes, in some sense, yes. But, and here's going to be a long quote, which you don't have to read now if you want to get the slides later, but in some sense also no. I could give you a moment to read this, but what I want to take away from this is something, again, that blew me away when I read it, because you have to really think about what this means. Our brains do math and read, but neither one of those functions are things that our brains evolved to do. Let me try saying the sentence differently. So our brains evolved to match certain functions that we were doing, but math and reading were not two of them. We use parts of our brain to do math and reading that were not evolved for those purposes, which is really interesting because who's doing that? There is one small part of the brain, which I'll talk about in a second, called the intraparietal sulcus, test on this, which is closely correlated with counting and subitizing. Subitizing means recognizing a quantity at a glance, like when you see 3, you know it's 3 without counting. But for the most part, everything that we do with math is the brain co-opting different parts and using it in ways for which it was not quote-unquote intended. Dehane calls it neuronal recycling. I think that's just amazing. And it raises really interesting questions about the mind and the brain. If any of you have read any of these studies, especially by Jeffrey Schwartz, who has a great book called The Mind and the Brain. He works with OCD patients, and he images their brain and shows these overactive electrical circuits which are correlated with activities they do repetitively and obsessively. He leads them through some meditative exercises where their mind, they choose to do something else, like read or garden or go for a walk, and over a fairly short period of time, 6 weeks in some of the studies, they rewire their brains and they quiet down the overactive circuits, the thickness of the neuronal linkages around those circuits is pared away, and they create a different pattern, which led him to the conclusion that your mind can change your brain, which is really fascinating, just thinking about that. But that is what all of us do when we read and when we do math. We are using our brain, we're choosing to use our brain to do things with those parts that are there that they did not evolve to do. What is number sense? It's one thing if someone tells you that it's really not meaningful to speak of a math limit, and that really we can all develop our number sense. But what is it? How do you do that? And what Dehane and his team, and of course others, because it's always a collective global effort to some extent, but Dehane is credited with this finding, found is it's the ability to tell the difference between less and more. So to compare magnitudes. So for example, if you were to look at the box on the left, is there more green objects, not area, but objects, or more blue? Now, by the way, you want to call out what is on the left? Are there more green objects or more blue? Green, okay. When Dehane leads workshops, which I have the privilege of going to, one of them, he starts with these large screens where the discrepancy is wide, and so everybody can tell. And then keep seeing shifting constellations of these objects, and as you can see, he's not controlling for size, right? It doesn't matter if they're big or large, it's just how many. And as the discrepancy becomes smaller, as the difference becomes smaller, fewer and fewer people can tell the difference. Well, it turns out that that ability correlates very closely with what we call number sense. The ability to manipulate quantities in your head, to visualize them, move them around, decompose them and recompose them. And it's this ability, if you could grow it, that allows students to become better at manipulating math concepts. The figure on the right is actually about area. Is there one more green area, one more blue area? What do you think?
Green.
Green, okay. So this is one example. Now, Brian Butterworth, who was another person who's done a lot of work in this area, uses tests that are very similar. On the top, for example, if you look at those two yellow squares, can you tell how many without counting? If you can, that's called subitizing. So if you look at the left and you just see 4, but you don't have to stop and count them out, that's called subitizing. And children who are diagnosed with dyscalculia, again with all those caveats about not knowing all the factors that impact it, have a very hard time doing this. Even with what might seem like small numbers to us, they will typically count out each one and have a hard time subitizing. And again, on the bottom 2 squares, a little darker yellow, which side has more, left or right? Right. Okay. Again, children with dyscalculia, that diagnosis, how that's come to be, will have a harder time doing that. So that seems to be the piece that leads to what we observe and what we call anecdotally believed number sense. So how do you fix it? If any of you are familiar with some of the early programs that were done for dyslexia, created for dyslexia, that were based on the fact that students could not discriminate between sounds, and therefore they couldn't read them because they couldn't discriminate them auditorily. There were programs that elongated those sounds artificially, and then as students could hear those big differences, they ratcheted back the difference until they could hear smaller ones. Here, there's a similar principle used in a game that Stan DeHane created, which is a free download. It's called The Number Race. All you have to do is, if you're interested, Google it, The Number Race. I think it's actually thenumberrace.com. He's on a few different sites. And on the right, what you can see is the screen where the students will see different number of magnitudes, and they have to click on the side that has more. And initially, the discrepancy is very obvious, but slowly, the discrepancy gets harder. And one of the nice things about it is that it is designed so that the students always succeed 75% of the time. So you're still building confidence, even as you're going at your own speed. And then it mixes up shapes with digits, with words, so that you're playing with quantity in many different ways. And according to his research, even, I know it sounds hard to believe, I exhort you to go look at his website and read results for yourself. Even using this 5 minutes a day for 2 weeks will show some growth in number sense. Now, DeHane is the first to point out in his book, The Number Sense, you don't have to use this software to increase your ability to discriminate between quantity. You can use estimation jars. You have a big jar of stones, or if you want to start with pine cones, or any kind of an object where you, in a classroom or at home, have a student estimate how many do you think are in there. And they make an estimate. And then maybe you take out a small sample and count that and say, well, this sample is 10. How does that change your estimate of what's left? And you can do that over days. I've seen people do that in classes over days. It's great to see how the kids are really thinking about quantity, comparing magnitudes. So this is a kind of activity you could do at home. And this does grow number sense, which then helps the students in the class to perform on math-related tasks. By the way, it's never too late. But you can imagine how tedious it would be for someone who's 17 or 35 or 50. There is some part of the brain that is closely connected to counting and subitizing, which is this thing called the intraparietal sulcus. If you ever go on Jeopardy and you get that question, now I just realized I have to go over time a little bit. Is that okay? But we built an exercise, yeah. So we're good. One of the things I find fascinating is that even in these very rare cases where some children have a slight deformity in that intraparietal sulcus, now he's calling it the IPS, so you're in the know, so now you know what that means. And there are cases, there's something called Turner syndrome, where females might have an X that's slightly diminished, fetal alcohol syndrome, in some cases of prematurity. Even those children, using the number race software, grew the connections around that part of the brain and showed increased understanding of number. So it can work even in those cases. Okay, I'm going to forward a slide coming up with a lot of text, which I'm going to gloss over, and you can again read it if you would like to email us. I'm putting this up here for people who are specialists in particular, but for anyone, for parents too. Those students who you teach them something, a math concept, and they seem to get it, and then they don't remember it day after day, month after month, year after year, they're saying, don't focus on that kind of repetition because it's tedious for everybody. Instead, build foundational number concepts first. I do think if we really did this across the board for the whole country, we'd like have to have a week off, for everybody to go do this. But that's an interesting idea to keep in mind, that it can be done, and you might not see a change in the Groundhog Day effect unless you do this. Now, of course, at some point, you can say, I need to go on with my life, so I'm just going to use a calculator, and I'm going to have accommodations, and I'm not going to rebuild my number sense. Fine. But I just wanted to put it out there that it can be grown. Okay. Michelle Mazzocco works up in Baltimore. She was part of a project called the Kennedy Krieger Math Skills Development Project. I'm putting this out there just as the flip side of this argument. She identified with her team a set of students who, in kindergarten who had weak number sense. And she followed them for 13 years through 12th grade, and it never kicked in. So if DeHaene is showing us that you can grow number sense, you need to perhaps be aware of this study, which shows you that in the opposite case, where someone did not get any remediation or intervention, it did not kick in. In fact, there were significantly greater dips at certain grade levels, in 4th grade, and 6th grade, and 10th grade. So that's a cautionary tale. Yeah.
So she didn't find that the training made a difference?
No, the opposite. She intentionally did not use the training to see if number sense would grow. If you took a cohort of students who identified as having weak number sense in kindergarten and then watched them over a period of 13 years through 12th grade, would it kick in for some of them? Is it something that it kicks in? And it did not. Now, I'm not going to comment on whether there were what environmental factors may have contributed or not contributed. And I mean, when I usually tell this story, I find it kind of heartbreaking, actually, that you would watch kids for 13 years to do that. But it does prove that if you don't remediate, it won't improve. Yes?
So how does this relate to maybe a child who's, what they call it, has an algebra brain, somebody who algebra comes to very easily, but then geometry is, you might as well just not get in class for it. How does this relate to that?
I'm actually going to, and I'm not trying to pass the buck, but I'm going to let our middle school math teachers speak to that, because my hunch, and of course I wouldn't know unless I worked with the student, it would take a while, but that it might be that it's a different concept. So there might be a language-related issue, or it might be a spatial reasoning issue with this geometry. But that would be an interesting case to examine. I'm going to let Robyn speak to that. We'll get there. Okay, so that was the first big takeaway. That there is this thing called number sense. We've identified, I wish I could include myself in their group, we've identified what it is and how to grow it, and if we don't grow it, what the consequences can be. The second big takeaway is the role of emotion, as I mentioned, in mathematics. And not just the anxiety that you feel after the fact, which we know can cause people to panic and have a lack of oxygen flow to the brain, all those things, but actually leading up to it, that if you are excited, that's the flip side, right? If you're excited about numbers, if you're invited to think about numbers, if you have confidence about your mathematical thinking, this will directly correlate with your math success. So how important it is to not communicate anxiety about math. Because if you communicate anxiety, and there's been a number of studies showing that there was a group of 4th grade teachers who were studied, not here, and they identified as being anxious about math, but they never told their students that. But their female students, more than their male students, picked up on it, and they did worse. Emotion is critical. You can do this. Let's figure this out together. If you don't understand it, ask a question, get help, look it up. Let's get out some objects, move them around. But to always assume to be mindful of how important devotion is. And I just have some cartoons here about how, if any of us have ever been through this before, how we felt when we were wrong and how sometimes we feel like we can't go on. Leap of faith. I always tell my high school son, do you really understand this? Yeah, I get it, mostly. No. You have to really understand it, because if you don't and you take that leap of faith, it's going to be a problem later on. You have to really let yourself experience it and ask every question so you understand. So going back to Dehane, again, I told you that was surprising to me. I mean, he was Mr. Science to me. He's the guy, this beautiful, huge lab in Paris. He's known all over the world for his scientific studies of math disabilities. And he says, biological factors don't weigh much when compared to the passion for numbers. Great anecdote. Apparently in the 1800s, there were these shop girls in the Beau Marché in Paris who used to measure lengths of fabric in centimeters and millimeters. So we're talking some pretty big numbers. And they were brought from farms in the surrounding area, and they didn't have an education at all. And someone came from Oxford who was a math prodigy and was watching them calculate in their head, and saw that they were calculating faster than the people who he worked with at Oxford, who were also considered prodigies. Although that's just, and Dehane mentions that in his book. And there it's not maybe passion initially, but just practice and familiarity, comfort. It's a similar idea. Again, I'm going to pass over this so I can move on to my friends in 1 second. Hold on. So I'm now going to make a segue over to our two McLean representatives. Sarah from lower school, Robyn from middle school. But I want to just quickly frame it for you. So how do we at McLean think about the math classroom, math pedagogy, to both build number sense and encourage a positive attitude to math? So we do many, many things. We individualize instruction as far as possible based on a student's learning profile. We don't do one-on-one, we have small groups, but the teachers are aware of how their students learn math. Frequent formative assessment, meaning that feedback loop. You see what students are doing and you're giving them feedback. There's student reflection, breaking it down, taking difficult concepts like we saw in that first word problem and taking them apart. What are the ideas? What is the language? What are the symbols? Hands-on learning, we spoke about that. Project-based learning when we can. Real-world applications, and fun and games. But, and here's my major takeaway for myself, and then I'm going to pass it over to Sarah and Robyn. Building number sense and creating a good emotional environment are critical, but there is undoubtedly now another piece. I used to do all of this in order to make my students understand math. I was so happy to create a game called Passport to Hundreds. So they could see that hundreds in a fractional form, like I said, they speak fraction language on this island. Here's hundreds in a decimal form, that's what they speak on this island. And over here they speak hundreds on the percent island, because that's all they speak, that's all hundreds. And then here's how they talk to each other. I was so excited. Oh, I made this clever. I got them to feel not afraid. And now it's a game. And I think that was good. But you have to create what Joe Bowler calls a mathematics mindset. You have to create the conditions for them to make those associations. And not only give them the fun things that can excite them, but to build it from the ground up. And that's what I think we do very, very well. And Joe Bowler, who is known for this phrase, I took it from her, Robyn mentioned it to me, ran a summer camp using this kind of mathematics mindset, teaching, nurturing the kids from the ground up to play with numbers and ask questions. And you can see the improvement in every range of ability. And I think that this is really key for good math instruction. Now, which means that providing a good emotional environment does not have to diminish rigor. And too often people think, oh, if you make them feel good about themselves, it won't be rigorous. But if you develop a mathematics mindset, okay.
All kinds of things. But the basic puzzle is relatively simple. So your goal is to get all the rings from here to the other side, and there's 2 rules. You can only move 1 ring at a time, and you can't put a bigger ring on top of a smaller ring. Okay? I had a lyrics for each fact, like 1 plus 9, we're doing fine. 2 plus 8, I forget what it was. But and what was interesting, and then we added music. So here's where here's where they're kind of at the last step at the end they presented to the kindergarten. That's kind of the culmination event. So here they know the song, they're practicing with the instruments, and there's research about how having that steady beat helps you learn as well. It changes some of the brain waves in a beneficial way and things like that. And what was interesting to me is that a couple of the students that really struggled at the beginning of this and really, even with the tense frames, weren't understanding how to get 10. At the end, when they were doing, one of them I worked with, and she would say the line in her head, and that would help her get the answer. So that was really cool to see. And there's many more ways we incorporate multi-sensory learning. Okay, this is just a snapshot. Okay. So this is another thing about a different way of practicing facts. So this is a worksheet / game that comes from the Do the Math series by Marilyn Burns. So we incorporate a lot into our teaching, especially in the lower school. So what you're doing here is you have 5 double-sided discs, and you're shaking it up and putting it over. Okay, so I got 5 red, so that would be over here. And I would write 5 plus 0. And sometimes students would have OT issues or anxiety, so I'll either write for them or we'll just check off the box. So you're practicing 5's facts, numbers that add up to 5, but there are a lot of things about this that make it much more beneficial than a traditional worksheet. First of all, the hands-on multi-sensory aspect. The fact that they can see with the color. Oh, I forgot I can't touch the screen. Okay, so they can see. Oh, 3 plus 2 is the same as 2 plus 3. They can see that addition property. Also, I mean, it's actually kind of unusual. I got this because these middle ones are way more common than these. And you can kind of start to have a discussion about that. You can predict which one goes to the top. Not only are you practicing numbers, and there's actually ones for higher numbers too. And I've even made one for higher than even Maryland, for instance. So it doesn't have to be just 5s. But not only they're practicing in facts and making all these connections, you can have, they're learning probability without knowing rigor. They're learning probability. They're learning kind of what a bell curve is. I mean, we don't talk about that language in that way, but they're getting that at a young age. And when they come back to it, they'll be more familiar with it. And again, the element of fun and, especially if we're just checking off the boxes, really should not be very little anxiety involved.
Question.
Yes.
This is across the board with mathematics, multiplication, division.
Well, there's different, and now this is frozen. We do things that similar to this in all facts. I'm gonna talk about multiplication in a second. I'm gonna go into more detail about that. You know where this goes?
I can help you do that.
Okay. Okay, so multiplication. All right, so the rest of my talk is focused on multiplication. So in the lower school, we introduce multiplication as arrays, which is basically rows and columns of different objects. And actually, this is at the representational level. We start with something at a concrete level. So we'll start with actual, Marilyn Burns has foam squares, or I like to start with Play-Doh. So they're actually making these first before they get to their representational level. And again, they're getting they see it, and they're making these connections. So they've all seen 4 plus 4 is 8. So you can talk about, okay, that's repeated addition. And that's the same as 2 times 4 is 8. So they can make more connections, and just that visual way of seeing multiplication facts, which I don't ever remember doing when I was a kid, really helps. And making more connections, it makes more, it's multi-sensory. Okay, it's still not working.
Okay, I'm switching it there. Sorry.
I don't think I did anything weird. Okay, so, and this is just an example of something you can do with arrays. To practice them, you're incorporating art, which like music has a lot of benefits to learning. very low pressure activity. You know, you don't have to write anything. You're making a full picture, but you're still practicing arrays. Okay, we're going to show the, now my assistant. All right, and then this is a multiplication game from the Marilyn Burns series. And it's basically like the card game War. So each person puts down a card with an array on it. So this person's is 3 by 3, and this person's is 2 by 4. And whoever has the bigger number wins the card. So it's like traditional War. What is great about this, besides again they're seeing the arrays and practicing that, it goes beyond that. It's even richer than that. They're comparing. This thing does not like me.
Now you know how to move it, right? Just touch the board.
Oh, just touch the board. Okay. I'm so used to like drawing on the board and stuff. Okay, so and again, it has the element of fun. It's a game. It's fun. There's no pressure to write things down, especially with third graders. We have a second, third, fourth when they're practicing this. We have a lot of students with OT issues, and they really avoid writing or it's stressful for them. And they already have to do that in a lot of classes anyway. So anything like this where they're practicing the skill, but you're really focused on math. You're not focused on anything else. Okay. Wait, it's not gonna work.
Now for dinner.
There we go. All right, the other thing that's very different from how I learned math facts. So when I was in third grade, I remember we all had, everyone in my class had a sheet that went 0, 1, 2, 3, 4. And when we mastered each number, we colored it so and we went in order, okay? What we do here is we start with the easiest facts first. So 0 and 1 are very easy. Most people don't have to practice those very much. Students in second grade, maybe even first grade, practice their doubles facts, 7 plus 7, 8 plus 8. So they're very familiar with this. So multiplying 2s is really not that much of a leap from what they've already done before. Counting by 5s they've done since kindergarten. So it's very easy, or relatively easy, to explain multiplying by 5s. Same thing with 10s. And then 3s and 4s are easier than the 6, 7, 8s. It's easier to count by 3s or to do the double and one more, the double, double. So those are easier. So we start with those. Another thing I wanted to point out is that it's okay. Nowadays we have research. Actually, Joe Bowler, that Linda mentioned that we all worship, did research. She's a Stanford University mathematical educator. She did research about how this is not only okay, it's beneficial. And if you shut that down, it's detrimental. So you can teach 9 facts, and again, I don't remember learning this. You put down, so here you have 9 times 4, so you put down your 4th finger, and then you 36. You see it's 36. So that's kind of a new thing that was not known, even 5 years ago? However long ago. Another thing we do to help students remember the harder facts is with mnemonics. So for example, 8 times 8 tends to be a hard fact for people. So there's many of these, but this one is the one I always remember. I ate and I ate, I got sick on the floor. 8 times 8 is 64. They learn that, they'll remember it. They'll remember it. And there's another one here, but we'll pass that. Okay. The benefit to using easier facts, or learning the easier facts first, is that you can then use those to figure out harder facts. So for example, 12 times 9, most students will freeze and think that is so hard. And then you go, well, what's 11 times 9? And they know that, and then you can add another 9. So that gives you a strategy. Same thing with 7 times 7. Students stress out about this one. And you say, okay, well, 7 times 5, right? And then you can add another 7 or 2 7s or 14. The other thing about doing this and making all these connections and the flexibility of thought is it can make other things more easy as well. So if I was just to go in order here, 5 times 7 is 35 times 5, if I had to, I could figure it out. But if instead, I look and see, is there an easier way of doing this? And I could say, okay, 5 times 5 is 25, times 4 is 100, 700. Way more easy, okay? So if you teach, and this kind of flexible thinking helps a lot with algebra as well. So and if you do that, they're able to make these connections. And again, it's also fun, hopefully, and it's more, it's harder in a way, so it's sort of more rigor. I don't know if that's me or whatever. Okay, so also if you do that and you teach multiplication this way and talk about strategies and figuring out strategies, kids can come up with strategies. And this is an example where I had a second grader. He didn't know, this was at the beginning of this year, he didn't know multiplication, except that he knew twos were doubles, so he could do that. And I have these hot dot flashcards I'll show you at the end. He really wanted to do multiplication, so I said, okay. Other kids are practicing addition, subtraction. He's like, I know all that. So I said, okay. I was trying to hand him the easier ones, the 2s and the 5s, and then I was helping another kid. And he came upon 8 times 8. And I said, you know what, that's a hard one. Let me know if you need help, or you can skip it, because you haven't learned that yet. Instantly, without even thinking, it seemed like, he said, well, it has to be 40 plus 2 12s, so it must be 64. And I sat there going, huh? How did you get that? And he wasn't very interested in explaining his thinking because he wanted to move on. From what I could figure out, this is maybe what he was thinking, that he knew his 5s facts. Oh. I haven't practiced this thing. Okay, so he knew his 5s facts, and that was 40. And then he must have known, well, I don't know 3 times 8, but I knew 3 times 4, which is 12. So if I do that, it's the same as 3 times 8, and 40 plus 12 plus 12 is 64. Although he got this so fast, I'm not really sure if that's how he got it. But it was one of those things that I had to sit there and go, I would have thought of that, and I've never had another student think about that. But it's great. It's such great mathematical thinking and such great mathematical mindset. Okay, so the last slide I'm going to show you is that even with more traditional ways of practicing math facts, nowadays there's better ways of doing it. So, for example, flashcards. These are interactive flashcards. So you have a wand, and it will tell you if you're right or wrong. Okay. The other benefit to this is you get feedback right away if you got the right or wrong answer. Versus when I was a kid, you'd fill out a sheet of facts, get it back the next day, and so this is much better. Also games. I mean, this is multiplication bingo basically. You're just practicing facts, but there's no writing involved. It's more fun, and even multiplication and more. Most kids love this. So again, 4 times 8 is 28, 5 times 8 is 45. So this person would get these cards. Maryland Burns actually makes cards that just have the number in case students are distracted by these pictures. But I find most students are okay without that. So anyway, thank you. And I have stuff up here if you want to look at after.
We could talk all day.
Linda was talking about counting them versus seeing how many there were without counting. And then Sarah just told you the story a few minutes ago about her student who was trying to get him to explain how he arrived at something. So if we put those together, this sort of leads into where I'm going to go with this. So something that we've been doing in the middle school is dot talks. Has anybody experienced dot talks before? Okay. Good. A couple. So, and I'll give you the resource, the book for this, Kathy Humphreys, at the end. So what I would do is I would introduce this and say, we're going to have a dot talk today. I will flash a picture, and so normally you wouldn't have the opportunity to see this for a while. I'm going to flash a picture. I want you to be ready to tell me how many dots there are, but try not to count them. So I would flash this, and then I would say, how many dots are there? So how many dots are there on this? 7. Okay. And so there was a little hesitation there, maybe, and especially if I flash this and then take it off. Some students, I think I saw 7, but I don't want to be wrong. I don't want to. So this is helping to build that confidence, and that idea that everybody's going to see something a little bit differently. There's validation involved in that. So we do this, and then I would say, how did you picture those 7 dots, or how did you see those 7 dots without counting the 7 dots? So does anybody have an offering, how you can picture this?
I see the 5 like on the dice in the middle and then 1 on each edge.
Beautiful. Okay, so these 5 sort of in the center, and I love the way you describe that, like on a die, because that's something that we know we can relate to, and then 2 more on the side. Anybody have a different way of seeing them?
I see the 5 on the bottom, like the Olympics.
Okay, great. And again, thank you for giving something that we're familiar with to see that. So I would ask a lot of students to do that, and I would actually draw those shapes up there. And so this is an example of when we did this one day. It was the same dot. This was actually way at the beginning of the year. And so all of these are different ways of seeing those same dot configurations. So again, this is validating that everybody is seeing it a little bit differently. I would also ask, and so these were the answers that I got first. Some people saw 5, some people saw 6, and then 7. So those were the numbers. It was safe for them to call that out because this is just how many dots there are. I'm not saying you're not good at math. I'm not saying you don't know how to count, all of that. And I love too that in this case, one of the students who had a wrong answer was willing to share how he saw that and why he was seeing that incorrectly. So the next step then, after drawing these, is to make a mathematical connection to the patterns and things. So one of the ways you might see it is 3 separate rows. Some people saw 2 on the top, 3 in the middle, 2 on the bottom. This is the expression 2 plus 3 plus 2, okay, which then gives us 7. Some people saw 2 diamonds that connect in the middle. So this is 4 plus 4 minus the 1 that's repeated, or this could even be a multiplication application, 4 times 2 and then subtracting the other one. Order of operations, all kinds of things come from this. Again, based on how you see that. Another one was the hexagon and then the 1 in the center. So I did this with Joe Bowler in California this summer in a room of, I think there were about 100 math educators. We came up with 36 different ways to see this. And what's nice too is as you're going through this, you put that dot drawing back up and you start to see other ways of looking at it and other ways come out. And students get very excited being able to share that. It leads into actual number talks. So again, I would put this problem up, 18 times 5. Ask you to do this mentally. Don't write this down. 18 times 5, mental math. Then I would ask, how do you see that? How did you come to 90? So some people may have just the traditional algorithm. 18 times 5, to use language that may be outdated, carry of, the 4, all of those kinds of things. We then put a visual picture with this. So you might say the more algorithmic way, the 5 times 10, 5 times 8, 50 plus 40 is 90. Shown in a rectangular visual representation, you have the 5 and the 10, the 5 and the 8, all together, there's your 90. If I ask this question, how did you see that, or how did you arrive upon that? Somebody may realize that you can round your 18 up to 20 because 5 times 20 is a quicker, more accessible fact, and then subtract the extra off of there. Okay, this leads nicely. You can use that with rounding. It also is a visual for the distributive property, as well as the first way. But distributive property, of course, as we get into algebraic thinking, is going to be really important. Again, it's very accessible and it's non-threatening. And when I've offered these, students invariably come up with ways I hadn't even thought about to justify their thinking with this. You might have 10 times 18 and then take half of that. And so that gives us a really, I think, a very valuable way of seeing where the number sense is in the students, much more so than a fact sheet or something like that. I can really see where their thinking is, why they're coming up with answers that they are. So something that I do in the middle school a lot to continue those manipulatives, the very tactile, we move into, I use an Algebra Tiles app. I also have the actual Algebra Tiles manipulatives. my students sometimes will choose to have the actual tiles. A lot of them really like the app. We were able to put this app on all of the iPads for 7th and 8th graders this year, so we use this for several things. This I would call you back to the race to the top. So it's similar with the yellow and red counters, except that in this case, when we have yellow and red together, they form a zero pair. So we don't use the language cancel. We say it forms a zero pair so that they are actually learning that a positive and a negative go together to make this other very, very real number. It's zero, has a value, and that's something that's very hard to understand if that number sense around the value of zero isn't built early. So that's why I like something like this. We could do race to the top, but with positives and negatives instead of with the just the addition of the positive integers. We also use algebra tiles to show the pan balance problems. Sarah reminded you that this is a very algebraic way of thinking, and so we take that and build on it and do make that connection. We have the same pan balance here, except that instead of the very friendly umbrellas and ice cream and strawberries and things like that, we have this, these scary X's. But this allows me to take it back down to them, and very often we will say to them, you guys did these things, when you were in 1st and 2nd grade, and you probably didn't think, oh, this is impossible, I can't figure this out, because it was fun. All of a sudden, when you call it algebra or you put an X in it, it becomes very threatening. Threatening sounding to people, but it really is the same. This app, again, is lovely because this eyeball down here, I can hide what's actually on there, but then you can expose it again. It doesn't solve anything for them. We go through the steps of how you manipulate these, and that's the next step in this learning process, but it really is a nice continuation of that. It makes the algebra very concrete until you learn how the numbers are relating to one another, how the variables are relating to one another. And then again, the goal is to move away from having to use the manipulatives, but this forms that bridge in between.
I've got a question, I'm sorry.
Yep.
Can you go back? Where are these apps? Can we find these apps?
Yes, and we'll have, at the end, we have some resources for you.
Great.
This one is a braining camp.
Okay.
And I believe, if I'm not mistaken, was it $1, $2
It's not
for this? I mean, it's.
Okay.
And you can also email us, we have a lot more.
Okay. Going back to the array multiplication. So this is our continuation of the array multiplication in middle school. Again, instead of the tomatoes or Play-Doh or whatever, we can scaffold this. It's still very manipulative. Okay, we start with the actual plastic tiles, but we'll lay it out on this type of array here. We would use this to lead into matrices, so rows and columns, and then also to continue that multiplication of integers. You can do this with negative integers, or, and I love this, you can add in the variables. And polynomial multiplication, which again sounds very abstract and very threatening, is a simple array set up exactly the same way as the ice cream cones or the apples or whatever it was that they did years before. And this then can go backwards when we are factoring polynomials and things. Again, we can take it back to, it's a very visual connection. Again, multisensory, all kinds of things. I will have students say that the tiles just don't work for me. I'm not visual. And we'll say, but the tactile, with the visual and the auditory, it all goes together. And this part has been mind-blowing since we discovered this and have been using this with algebra students. If it's a continuous process throughout lower school and then middle school, just building on all of these types of things, that number sense piece is in there to where that foundation is set, and we're able to work with these things and they can move forward with that. Do you want to?
So we have to make 0.66 or 6600s into 3300s.
Yes.
So
So again, yes, imagine this. So take yourself back to coming in the room and seeing this problem, and we touched on, of course, the anxiety that comes from it, the completely irrelevant type of, you don't order pizza this way. I'm going to be completely honest, when Linda said if you want to stay after and see how this is solved, even I don't want to stay after and see how this is solved because it's not, and I love math. Math excites me, the numbers excite me, and this does nothing for me. And when I'm very guilty of this, I have given these types of problems because it's easy, they come in books, and they're, maybe not quite this extreme, but, we give these types of problems and then we can't understand why students aren't excited about it, why they're not learning it, why they're not putting the connections together. So instead, I offer that we start with a prompt like this: compare 6 divided by 2 to 6 divided by 1/2. So this was similar to something that I put on the board as just a prompt with students the other day. And it was amazing the depth of the conversation that came out of this, and then the forward movement that the students took with it. Again, it's low risk because you're comparing two things. You're making observations. There's not always a right answer and a wrong answer, and so I like to throw out problems or situations where they can think about it and where they can discover things on their own. I had, like I said, one similar to this the other day, and a lot of the class I asked just for a silent vote first, how many of you think these are equal? How many of you think these are the same? So I had them do a thumbs up, thumbs down, just kind of in hiding. So are these equal? Thumbs up? No, thumbs down. Okay. And so a lot of students, had a quick, and of course I have a fair number who like to be non-committal and still, kind of put the, or hide. And finally, one student said, these can't be the same. Those numbers aren't the same. 2 is not the same as 1/2, so they can't be the same. And that was when a few other students kind of went, oh, huh. So I didn't validate that, didn't say you're right, you're wrong. What do you think about that? Then I invited them to show me this visually. Who can draw a picture that shows 6 divided by 2 versus 6 divided by 1/2? And that became a richer, bigger task. But again, it was interesting as they started putting things up there where every single student in that class wanted to come up to the board and draw a picture showing this. Probably 80% of them were wrong as far as what they were representing was not that, but I just stood back in the back of the classroom and let them do that. And then the ones who seemed to have that, they knew it. They knew they really had it, and they wanted to stay up there and kind of convince other students why they were correct. And so we used the language of defend your answer and who's switching sides, and do you want to vote for that one or that kind of thing, to really encourage that positive feeling about learning mathematics, that different ways of looking at something are valuable. I don't have all the answers or the way of looking at something, and none of the teachers do, and so it is valuable to gain that insight to be able to assess, do they have a working number sense, a working ability to identify relationships between numbers and what happens with them.
Thank you so much. I don't know if anybody's itching to get up and draw that. I remember learning division by fractions with an algorithm, flip it, multiply it, but being able to explain it visually is a whole other thing and enjoy. Robert's class is a lot of fun, as you can imagine. Kids will take risks and figure things out. So we do have some time for Q&A, and so if you all want to come or up or just be available, whatever, we can talk about things. But the one thing I just wanted to leave you with is this idea that when a student asks for help with math homework or feels like they can't do it, what I would say to my kids, I'm just sharing something personal now, is well, whether you think you can or whether you think you can't, you're right and right. And so except for those really exceptionally small margin people who fall into that pool who have such a brain abnormality that they can't grow their number sense, this is something that we can all do. And we have to just remember that no matter what the evidence over years of struggle and agony seems to be that people can grow. Doesn't mean that it's easy, by the way. I liken this to weight loss. You can lose 30 pounds, you can become a marathon runner, but it doesn't mean it happens overnight. You have to be disciplined, you have to be disciplined regularly, you have to put in effort. So it doesn't mean that it grows like that, but it means that it's possible and it can be done if you put in effort. So.
And making mistakes along the way, by the way, is beneficial to growing your brain. There's been research and evidence that has shown that making a mistake, and even if you're not recovering from that, just the knowledge of the fact that you made a mistake does help to grow those connections. So we champion those mistakes. My students keep track of my mistakes. Which I'd like to say I put them in there on purpose, like the 6600s, but I don't, and I don't have to. There's enough mistakes up there, that they can catch, and we keep track of it on a Post-it board. But I found that they really do. They like to watch those mistakes, but I think it makes them more comfortable with taking those risks and being willing to try some things.
Also, that you actually can't learn some things without making mistakes. I mean, I always ask the kids, does anybody here learn how to ride a bike for the first time? Did they get on the bike and did they ride away? Of course, somebody always says that they did. They did. But it requires that balancing your weight, learning the way that the bike moves, how your body is in space. What do you think? Questions?
My daughters have like completely different learning disabilities. One seems to be able to learn the rules but doesn't have the math sense. One has the math sense but can't remember the rules. It's almost like they have you found that certain kids have different abilities in terms of how they learn math, or their ability to learn certain types of math, or how do you kind of understand that to help your child better?
You weren't the one who asked the geometry question before.
No, I was.
That was you. So maybe that's a time to bring that back in. Will you be there? You look shocked.
I was going to say one thing, and I guess this doesn't answer the part about how do you help to do that, although maybe it does. It is important for students to learn to identify where their strengths are, so that they can learn it in the way that is best for them. I'll sometimes say, who are my steps people in the room, and I'll kind of speak to them and say, these were the steps, but then address why those are the steps. So I very much know that I do have students who are memorizing steps. They're not to the point where they necessarily are putting all of those things together, whereas there are other people who need to know the why behind that. And I think, I'm not really answering the question, how do you do that?
Right.
But
because you'd want to have some kind of assessment, even an informal assessment of the individual student without being able to respond to specifics. Because intelligence is the space in between where I am now, wherever I am, with my strengths and my weaknesses wherever they are, and what I can do, what's in my power to do, to leverage them, grow them if I can, if they're growable, and get to what I want to get to. And I guess each student presents a different pattern of those things, and then figuring out how to get to the end. I know that's not answering your question directly.
What I want to know is how do I help the one who doesn't have the math sense develop the math sense, and the one who is not able to remember the steps? How do you kind of do that instead of working on their strengths? Help them do the opposite.
Sure. I mean, I'm just thinking as you're saying, the one who didn't have good number sense. So I don't know the age of that child, but I'm thinking of something like the number race. If they're young enough to be able to accept that game format, or estimation jars, or estimation at home, doing those little problems at home, go to the grocery store and estimating things and getting them to think things through in the car and talking. And then for the person who can't remember the steps, there are a whole other series of strategies for helping students to memorize, whether it's songs or mnemonics. And again, it's hard to answer the question in the abstract, but we have tons of resources we'd be happy to share with you if you'd like more specifics.
I also feel like it depends on the student, and I mean, for me to answer that, I feel like I'd have to meet your kid and see how they learn before I say, oh, this will help them. There's so much variation between different kids.
But there are a lot of resources out there.
But there are,
I think that's
yeah,
the bottom
there are.
line. I mean, it's worth trying.
and drawing that explanation out any way you can, and not to replace the show your work kind of thing, but, you know, what is your thinking? How are you seeing this? There might be very valid reasons that aren't steps that a student is applying or going through that you could kind of pull out and say, okay, this wasn't exactly these steps or the way I would have gone about this, but mathematically, it's okay. And then allowing that freedom in there, but also in someone who is memorizing steps, well, why did you do this step? You know, do you know why you're doing that? Can you explain it a different way? Can you show me a different